The topic is principal stresses. So to discuss this principal stresses, first of all I would like to tell you one important thing, that is types of loads, otherwise types of loading conditions. So we have different types of loading condition. Among I would like to discuss only some things. First one is uniaxial loading condition. Uniaxial means yet to consider is a member. So if this member is subjected to only one direction load, that should be along the length axis, then the loading you can consider as a uniaxial loading condition. Second one is biaxial loading condition. So same thing here, if the member is subjected to sigma x, that is in x direction, simultaneously it is subjected to sigma y, that is in y direction. You can call that as a biaxial. Like that we have triaxial also. I'm not going to discuss here. So simultaneously, if a member is going to be subjected to shear, so this is called pure shear. So this you can consider as a pure shear. And fourth one you can call it as a combined loading condition. Combined loading condition. So that is nothing but same thing, you can consider an element. So it is subjected to. So this is representation of tau xy, and here is also tau xy. Here it is tau xy, and here it is tau xy, and here it is sigma x. Simultaneously it is sigma y. Combined loading condition means it is having sigma x, sigma y, and tau x. So these four are the types of loading condition. Here I would like to tell you one thing, that when shear stress is subjected on element will be like this. So it is taken as positive. Remain case you have to consider as a negative, because this tau xy indicates that it is positive x. It is positive x plane and positive y direction. So this plane you can consider as a positive x plane, and this direction you can consider as a positive y direction. When both are positive, you have to consider as a positive. If you consider opposite trait, you have to take it as a negative. So it is the first thing, you have to know the sign conversion of shear stress. Second thing is let you consider any member. So it is a member. Okay, whenever it is subjected loading condition, you have to consider a small strip. Otherwise, this you can call as an element. Element always represented with a square member. So this total element I am going to represent. Whenever it is subjected to some loading condition, so same loading condition will be applicable for this small element also. So that's why you have to represent like that. So it is also subjected to sigma x, and it is also subjected to sigma x. And one important point you have to note down here is every plane has two stresses actually. So those are sigma and tau. So if you consider this is a plane, this is AB is the plane. So AB also having also two stresses. So those are already sigma x is you can see here, and also tau is existing, but the tau value is 0. So like that, if you consider any plane, you have the two stresses. So this is about the introduction, not related to the principal stresses, types of loadings, and the element consideration. And any plane is having two stresses, that is sigma and tau. Coming to the principal stresses, so before going to discuss, I will give some introduction. So let us consider a member. If this member is subjected to sigma x, and here is also sigma x, if I consider any parallel section to it, so on this parallel section also you have same sigma x. If the parallel section might be anywhere, okay, so that's why it can be called as a parallel plane. So on the parallel plane also we have same sigma x amount of stress will be there. But if you consider some inclined plane, this is an inclined plane. So inclined plane, let you consider PQ. So PQ is called inclined plane. On inclined plane, again this is one plane, right? I already told you that any plane is having two stresses, that is sigma and tau. So that is the only reason this plane, inclined plane, will have two stresses. One is sigma n, another one is tau n. Okay, so same thing I like to represent here. So I'm going to consider an element. So just if you consider a small element like that, square element, so I'm going to consider like that. And if I consider an inclined plane like this, so this inclination is theta, because from here to here inclination is theta. I'm considering in counterclockwise direction. So it is subjected to sigma x. It is again subjected to sigma x. But on this cross section, it is having sigma n and tau. So these two are the stresses. Here sigma n and tau n, you can consider it as a inclined stresses. Inclined stresses. So these are inclined. These are the stresses on inclined plane. Okay, on inclined plane. These are the inclined stresses on inclined plane. So like that, this sigma n tends to maximum somewhere else that you can call as sigma 1, and minimum somewhere else that you can call as sigma 2 based on change of theta. So these two stresses you can call as a principal stresses. So these two stresses you can calculate by using analytical method. Means sigma 1 and sigma 2 can be calculated by two methods actually. First one is analytical method, and second one is graphical method. So graphical method can be done by Morse circle. Morse circle. So here analytical method first. So analytical method means we have some equations, based on that we can conclude the sigma 1 and sigma 2. So let you consider a member. In that you have to consider element. So if the element is subjected to combined loading condition sigma x, and here it is sigma y, sorry sigma x, and sigma y here, and sigma y here. So this is tau x y, and here is also tau x. So this is called combined loading condition. So in this one, the inclined plane will be like this. So it is the reference axis, and this is the theta. So on this plane you have different stresses, that is sigma and tau. So the sigma n formula you can get as sigma x plus sigma y by 2 plus or minus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. Here you have plus or minus, and this sigma n comma sigma n dash. This is the sigma n formula, and again you have tau n formula, that is minus sigma x minus sigma y by 2. So it is sin 2 theta. It is also 2 theta plus tau xy cos 2 theta. So these are the two stresses. If you want to consider, you can consider this one, otherwise you can leave it. So these two are the stresses on inclined planes, and these are the formulas, because in the question itself he will give sigma x, sigma y and tau xy directly. If the direction will be like this only, you have to consider it as positive, otherwise you have to take it as a negative. So next thing is, if you want to calculate sigma 1, so sigma 1 is also having formula. So directly I can write sigma 1 comma 2 is equal to sigma x plus sigma y by 2 plus or minus square root of sigma x minus sigma y by 2 whole square plus tau x by whole square. So it is a principal stress equation. Simultaneously, this principal stress will be somewhere plane. The plane you can get it as on tan 2 theta p plane. So for this one, the formula is tan 2 theta p is equal to uh, tau xy divided by sigma x minus sigma y by 2. So here you will have the 2. So it is a theta. So again you have tau maximum also you will have. So tau maximum formula is uh, sigma x minus sigma y by 2 whole square plus tau xy whole square with square root. So it's a formula. So again this plane, this tau max is some other plane, so it is taken as theta s position. So it is minus of sigma x minus sigma y by 2 into tau xy. So by using these two equations you can calculate the position of two things. So just I will to draw the each and everything in a single diagram. So let you consider it is the element. So initially I am going to draw, this is called inclined plane, this is called inclined plane. So over it you have two stresses, one is sigma and another one is tau n. So let you consider somewhere else, uh, it might be anywhere actually, based on theta you will have the value. So let you consider somewhere here. So this is called principal plane. I can't say whether it is principal plane or not, but while calculating only you can conclude. So the inclination from here to here it is theta p. So the principal plane is having sigma 1. So perpendicular to it you have another plane. So it is also principal plane. So on this one you have some other stress, that is sigma 2. The tau over it is 0. So that's why principal plane also called as a zero shear plane. And some other plane you have to identify here, it is 45 degrees to it. So if you consider 45 degrees from here to here, so this is called maximum shear stress plane. It is maximum shear stress plane. So on this one also you have two things, that is sigma and tau. So this tau is tau maximum and sigma is sigma dash. So this sigma dash you can calculate it as sigma x plus sigma y by 2, or you can also calculate it as sigma 1 plus sigma y by 2. That is the only reason it can be called as average stress, average normal stress you can consider, average normal stress. So these are the equations by using the analytical method. So just I would like to go with the problem, then it would be very easy to use to understand all the things. So here is the element. So the element is subjected to different types of loading condition. So sigma x is 15 kilopascals. Here is also same thing, and sigma y is 5 kilopascals, and tau xy here it is tau xy is 4 kilopascals. So based on this diagram, you can conclude that sigma x is 15 kilopascals, sigma y is 5 kilopascals, and tau xy is 4 kilopascals. This is the question you had given. You have to calculate two things. So the first question is you have to calculate sigma n dash and tau n at a position of theta is equal to 40 degrees. So it's the first question. And second question you have to calculate sigma 1, sigma 2 with respect to theta p, and also you have to calculate tau max with respect to theta s. These are the two questions you have. So first I would like to go with sigma n. So sigma n formula is sigma x plus sigma y by 2. So it is the solution, plus sigma x minus sigma y by 2 of cos 2 theta plus tau xy sin theta. If you substitute everything in this equation, it is 15 plus 5 by 2 plus 15 minus 5 by 2 to cos of 80 degrees because theta is 40 dimension, plus 4 into sine 40 degrees. If you do this one, you will get the answer as 14810 pascals. Okay, so like that you have to do the sigma n dash also. Here you will have minus and here you have minus, and the answer you will get as 5190 pascals. So it is a thing. Simultaneously you can calculate tau n. Tau n is sigma x minus sigma y by 2 into sine 2 theta plus tau xy cos 2 theta. So again substitute everything. So that is 15 minus 5 by 2, here it is minus 16. Sine of 80 degrees plus 4 into cos of 80 degrees. The value of this one is minus 4230 pascals. You can take in kilopascals or pascals, that is your wish. So it is the first question. You can get the solution. And he mentioned data is equal to 40. Here one important thing is that you have to draw the element orientation. So how the element orientation you can observe, here it is x and here it is y. So this x is rotated with inclination of 40. Just you have to draw a line here. So here it is x dash. So this inclination is 40 degrees because we mentioned only. Here you have to draw the element in such a way that it should be perpendicular to this x dash. So we have to close like this. So on this section you have sigma n is 14.8 kilopascals. So here it is sigma n dash actually. And you have got negative value, right? So negative value means you have to represent like this. If it is positive, you have to close, means you have to mention the arrow in this direction. So the value is 4230 pascals. Whereas this one also you have to try with the value. So the first question is completed. Next, second question. B. So B indicated as we have to calculate sigma 1 comma 2. So it is sigma x plus sigma y by 2 plus or minus square root of sigma x minus sigma y by 2 whole square plus tau xy whole square. So is equal, here sigma x is 15 kilopascals only. I am taking in pascals. Plus sigma y is 5 divided by 2 plus or minus is square root of 15 minus 5 divided by 2 whole square plus 4 whole square. So the answer for this one is 16.4 kilopascals. So simultaneously, if you want to go with sigma 2, so sigma 2 as 3600 pascals. So you can convert it as 3.6 kilopascals. So same thing, here you have to calculate theta p also. How you will get tan 2 theta p is equal to tau xy 2 tau xy divided by sigma x minus sigma y is the formula only. So from this one theta p you can get, if you search everything in this one, the theta p you got the value is this 19.3 degrees. So for this one you have to draw the element orientation, same thing. It is x and it is y and it is an inclination of x dash plane. So here the inclination is 19.3 degrees. So you have to draw the element perpendicular to it and you have to conclude it. So on this one you have how much? It is 16.4 kilopascals. So perpendicular to it you have 3.6 kilopascals. So these are the principal stresses. You don't have the shear stress over this cross section. Next, coming to last question, it is tau max. Tau max you have to calculate. So tau max is same formula from here to here. So that is sigma x minus sigma y by 2 whole square plus tau xy whole square. The tau maximum, if we substitute, so here you will get the value is 6400 pascals. So it is also written as 6.4 megapascals, sorry, kilopascals. And if you want to calculate theta s, so same thing here, calculation of theta s can be done by tan 2 theta s is equal to minus of sigma x minus sigma y by 2 into tau x. Same, you have to substitute everything in this one and you can conclude the value theta s is minus 25.4 degrees. So like that you have to conclude, and again you have to draw the element orientation for tau max plane. So So here one thing you have to do that sigma 1 also sigma dash also you have to calculate, that is taken as sigma x plus sigma y by 2. So sigma x is 15 plus pi by 2 is taken as 10, 10 kilopascals. Okay, so these two things you have to represent our element orientation. So it is x-axis and it is y-axis. It is oriented with minus 25.7, so you have to take below, and this inclination you have to consider as minus. This is x dash. So here perpendicular this one you have to draw a side and you have to close a square, and in this direction you have sigma dash, and here the tau is positive, so here you can represent it 6.4 megapascals, and here is also it is 6.4 kilopascals, and here is also sigma dash is 10 kilopascals.